Predict the chemical formula for the ionic compound formed by having calcium plus 2 ions and bromide ions, potassium ions and carbonate ions, aluminum ions and acetate ions, and so on. So when we're making formulas, right, the rule is the number of negative charges has to equal the number of positive charges to get a neutral compound. So if I've got calcium and bromide in a compound, it's going to be 2 negative 1 bromides to every 1 positive plus 2 calcium. If I've got potassium ions with a plus 1 charge and carbonate ions with a negative 2 charge, it's going to be 2 potassium pluses to every carbonate, and so on. Now, how do we deal with multiple polyatomic ions? Again, polyatomic ions are a thing. They come as a unit. So when I'm looking at C, right, aluminum acetate, the way I deal with multiple polyatomic ions is I put brackets around the polyatomic ion to indicate I'm going to have multiples of them, and then I put the subscript on the outside, right? So what this really means, right, when you have Al brackets acetate subscript 3 is you've got 3 acetates for every 1 aluminum plus 3 in the crystal. So what is acetate, right? It's a molecule. It's a thing. This whole thing comes as a unit. So to show that I have multiples of this unit, I put the brackets and I put the subscript on the outside. So that's how you deal with polyatomic ions. Predict whether the following compounds are molecular ionic. All right, so if it's a molecule, guys, it's made up of just nonmetals. Boron's a nonmetal, hydrogen's a nonmetal. So this is a thing, right? This diboron hexahydride would have 2 borons connected, and the hydrogens be connected to the borons. So this comes as a unit. We'll talk about how you know what's connected to what later on. But for right now, all you got to recognize is that if you just have nonmetals, it's a molecule. B, carbon's a nonmetal, hydrogen's a nonmetal, oxygen's a nonmetal, right? Hydrogen's in a weird place, right? It's not a 1A it's not a 1A metal. It's a nonmetal. So again, it comes as a unit. This is methanol. Methanol is a thing. These are connected by covalent bonds. Now, when you hit C, as soon as you see a metal, it's a cation, guys. That's all metals do in chemical reactions is lose electrons. So if you're looking at lithium nitride, it's going to be ionic. You're going to have lithium cations and nitrate polyatomic ions. So what you guys got to get used to doing is seeing the nitrate in the formula, right? NO3 minus is a molecule with a charge. So for every 1 lithium plus, you've got 1 nitrate in the crystal. I mean, this is what this thing is, right? It's lithium ions surrounded by these molecules with a charge, nitrates. Scandium oxide, right? Scandium's a metal, oxygen's a nonmetal. Guys, you can never have a metal with a metal. So as soon as you see a metal, it's an ionic compound. So ionic, no nonmetals in there. And again, you've got to pick out the polyatomic ion there. That OCl. No, I take it back. It's not. Forget it. That's not hypochlorite. That's a molecule. That's a molecule. H, right? Silver. Silver is a metal, so that SO4 is the polyatomic ion. It's SO4 2 minus. That's sulfate. So again, you got to get used to picking out the polyatomic ions when they're matched up with metals. Give the chemical formula for the following polyatomic ions. Well, on the AP exam, they don't give you a list of the polyatomic ions. I do a lot in class just to get you guys used to looking at these polyatomic ions. But the way to figure out what the formula is for the polyatomic ion is to memorize the 8s. All right, so sulfate and chlorate are not the same formula. There's no pattern, right? So the only way to figure, to know what the formula is for chlorate is to memorize it. So you get used to playing with these, right? ClO3 minus is the polyatomic ion chlorate. So if I want to get hypochlorite or chlorite or perchlorate, it depends how many extra oxygens or oxygens you take away. So if I'm looking at the chlorite, any ite has one less oxygen than the ate. So if I take one oxygen away from chlorate, this is where I get chlorite. Chloride is just the monoatomic anion that you get when you put an electron onto chlorine. So chloride. Perchlorate would have an extra oxygen. So if it's an ite, you're taking an oxygen away. If it's a per-ate, you're adding an extra oxygen. So chlorate turns into perchlorate. And hypochlorite, you'd be taking 2 oxygens away from chlorate. So if chlorate is ClO3 minus, hypochlorite would lose 1, 2 oxygens, and this is where you get hypochlorite. So you get used to it, right? Playing with these things. You memorize the ates, you can kind of deduce what the ites and the hypoites and the per-ates are. Name the following ionic compounds, right? So ionic compounds are easy. Just name the cation, name the anion. If you see lithium in the formula, it's the lithium cation. If you see oxygen in the formula with the metal, it's oxide. So it's the oxide anion with the lithium cation. Now, iron. Iron falls in this category of transition metals, right? If we're looking at the periodic table, if you're on one side of the staircase, you're a metal, right? You lose electrons, and in a predictable way. If you're in group 1A, with the exception of hydrogen, you're always losing 1 electron. If you're in group 2A, you're losing 2. If you're in group 3A and you're below the line, you're losing 3. On the other side of the line, it's predictable, right? I mean, if you're in group 7A, you're always taking 1 electron if you're reacting with metals. If you're in group 6A, you're taking 2. If you're in group 3A and above the line, like nitrogen and phosphorus, you're taking 3. So these are things we can count on, right? I mean, magnesium is always going to have a +2 charge because it's in group 2A. Bromide, if it's matched up with the metal, is going to have a -1 charge. Okay. The problem is transition metals. Transition metals don't follow a nice trend like the A's, right? Group 1A, Group 2A, B, 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 3A, 4A, 5A, 6A, 7A, 8A, right? The A's are what we call the main group elements. Pulled out from that are the transition metals. The transition metals don't follow a nice pattern. Sometimes iron, for example, can come as a +2 charge. Sometimes it comes as a +3 charge. The more likely one is +2, but hey, you do have the +3 around. So how do you deal with the fact that you have 2 kinds of iron, +2, +3? Well, the way we deal with that is we use Roman numerals to indicate which charged cation we're talking about. Are we talking about iron with the +2 charge? In that case, we call it iron 2. Or are we talking about iron with a +3 charge? Then it's iron 3. No, so we use the Roman numeral to indicate what the charge is. So that's the name of the cation. Iron with a +2 charge is iron 2. Iron with a +3 charge is iron 3. Copper with a +1 charge can come as a +1 charge. It can also come as a +2 charge. So if it comes with a +2 charge, you call it copper 2. If it comes with a +1 charge, you call it copper 1. Chromium. Chromium you can find is a +3, a +6, or a +2. These are the common ones. +3 is the most common. Chromium 3. Chromium 6, again we're using Roman numerals, and chromium 2. So this is the name of these cations. So when you see them in formulas like with FeCl3+, the clue is the chloride. You've got 3 chlorides. We know chloride has a -1 charge. So we must be talking about iron with a +3 charge. When we get to C, we're dealing with the hypochlorite anion, right? So if we know what chlorate is, take 2 oxygens away, you got hypochlorite, so sodium hypochlorite. I'm sorry, I messed up. I was just doing the transition metals, right? So when you get to E, right, what kind of copper are we talking about? I named it wrong. Oh. This is not copper carbonate, this is copper hydroxide. There we go, better. Try it again. back to what I wanted to do anyway, right? So looking at the formulas or the ionic compounds with transition metals. So hydroxide always has a -1 charge. You get that by memorizing it. So if you've got 2 hydroxides to every copper, you must be talking about copper 2. Looking at the one next to it, F, right? Iron. Nitrate's got a -1 charge, right? You memorize that because NO3 minus is the formula for nitrate. So we must be talking about iron 2. Calcium, we know it's +2. Chromium, right? Chromium can come as a plus 3 or +6 or +2. In this situation, since carbonate is always -2 and you got 3 of them, that must mean we're dealing with, and we've got 2 chromiums. This must be chromium with a +3 charge. So I would need 3 of these -2 carbonates to cancel out the 2 chromiums. So each of these chromiums must be the +3 variety. So chromium 3 carbonate. And then the rest, right? So gotta memorize the polyatomic ion names. Those are your clues as to what the charge is going to be on some transition metal. Write the formulas for the following compounds. A, aluminum hydroxide. Aluminum's got a +3 charge. Hydroxide's got a -1 charge. B, potassium sulfate. Potassium's got a +1 charge. Sulfate's got a -2 charge. So we'd need 2 potassiums to every sulfate. Copper 1 oxide. Well, copper 1's got a what charge? Oh, +1, right? That's why they call it copper 1. Oxide always has a -2 charge. So you'd need 2 copper 1s to every oxide. Zinc nitrate. Nitrate's got a -1 charge. All right, so this is one of these transition metals. We don't put a 2 or a 1 on zinc. Zinc is always +2. So again, they don't follow nice trends. Zinc is always +2, so you don't put the 2 in. There is no other zinc. Zinc loses 2 electrons. So this is the formula for zinc nitrate. Mercury 2. It's got a +2 charge. Bromide's got a -1 charge, so 2 bromides to every mercury 2. Iron 3 carbonate. Iron's got a +3 charge. Carbonate's got a -2 charge, so I would need 2 iron 3s to every 3 carbonates. Sodium hypobromite. Give the chemical formula. Give the name or chemical formula. Give the name or chemical formula as appropriate for each of the following binary molecular substances. Okay, so sulfur's a non-metal, fluorine's a non-metal. So in this situation, when you're naming molecules, you got to use counting prefixes to indicate how many fluorides are connected to that sulfur. So the way you name molecules, simple molecules, is you just name the name of the atom of the less electronegative element, which is sulfur, and then you put the more electronegative element second, and then an "ide." Use counting prefixes to indicate how many things are connected. So 1 sulfur, you don't call it monosulfur, you just call it sulfur. Use a counting prefix to indicate that you got 6 fluorides to every sulfur. So sulfur hexafluoride. So let's try the next one. Iodine is the less electronegative element, and 5 fluorine. So the counting prefix for 5 is penta. So iodine pentafluoride. Xenon, and you've got 3 oxides. So xenon trioxide. Dinitrogen. Oh, okay, so we're using a counting prefix with the first one because I have multiples of it. So 2 nitrogens, tetraoxide. 4 oxides. Hydrogen cyanide. And tetraphosphorus, 4 phosphorus, hexasulfide, 6 sulfides. That's how you name molecules, right? We use counting prefixes to indicate how many actual atoms are connected in it. Butane is the alkane for which a chain of 4 carbon atoms are attached, I guess. Write the structural formula for this compound. Determine its molecular and empirical formulas. I wonder if I did all this. All right, so if it's butane, again, with organic chemistry, has its own rules. We'll get into that later on in the course. But the structural formula for butane would be 4 carbons, and you'd have each of the carbons saturated with hydrogens. So the molecular formula for this is C4, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So can we write this in lower multiples? Yeah, we could divide this by 2. So this would be the empirical formula, right? The smallest whole number ratio. So notice with molecules, right? The empirical formula, as we're going to find out, is a stepping stone to get to molecular formula, the actual number of atoms. With ionic compounds, you just need the empirical formula, smallest whole number ratio. Chloropropane is derived from propane by substituting a chlorine for a hydrogen on one of the carbons. Draw the structural formula for the 2 isomers. All right, so we'll get into isomers and stuff later on in the course. You could put the chlorine on the end carbon, so this you indicate what position that chlorine was attached. So this is 1 chloropropane, or you could have put the chlorine at the number 2 spot. Call it 2-chloropropane. There is no 3-chloropropane. If you put the chlorine over there, you just call it 1, right? You're starting from that end of the compound. So wherever the substitution is, that's where you start counting from. Again, we'll get into isomers and isomerization with ionic compounds and the naming of ionic compounds later on in the course. Right now, in this point in the course, you should be able to name ionic compounds, molecular compounds, and acids.